Okay.
Wait, the
Am I
microphone. The
here?
microphone. It's
Okay.
no, it's working. It's okay. It's okay. It's okay.
Oh,
Okay. Now
yeah, I got another.
Okay, so now I will present the paper, Taxonomy of Manufacturing Joining Operation based on process characterization. Can you hear? Maybe the slides I'm not hearing it because I'm holding the look here. Oh no, okay, it's okay.
It's okay, let me know that if the slides are not visible.
It's okay with the slides.
But then Chungu will say, yeah. Okay, hello everybody. My name is Akupal Sarkar, as you all know probably now. And then this work I have done with my ex-advisor Tusan Sormas and my current supervisor Hedi Karai. And this is about building a taxonomy of joining operation. And so why we are doing this, okay, 1 second. Why we are doing this, of course, I'm not going into this importance of ontology. We have heard it so much and we'll hear again. But this joining operations are extremely important for assembly operations, and then assembly is everywhere in the industry. Joining operation, we can think as an atomic activity of the assembly operation, though assembly needs, many more other operations, for example, part handling, and then you have manufacturability, repairability, and all of this. But we will try to understand what is this atomic activity, which is the most important sub-activity of the assembly, assembling operation. But then I am also interested in this because my background is in process planning, manufacturing process planning, and there you need to actually find the right resource and the right process for your requirements so that you can make the product. So for that, a good taxonomy, which has all the process characteristics, is very much helpful to find the right process for your requirement. And of course, then there are other, let's say process quality control, and then cost, all of these other things we need to represent, and we can represent if we have a taxonomy which can give you a good definition of these joining operations. So now going into a literature a little bit. So of course the assembly operations were first talked to by this ontology, though it is not an OWL ontology as such, but open assembly model. Many people know that it was proposed by NIST, I think more than a decade ago. And then a very significant contribution came from Dr. Kim from Wayne State. And he actually focused on the joints, and he was able to define different types of joint based on some topological construct. But then in recent time, just 3 years back, I think there was one PhD, one doctoral thesis came up, which used, which was done by Gruher, and then she used this framework called Janus theory by Demoli. And there also, of course, they heavily adopted Kim's model, but then they proceeded on defining the joining operation, not only joints. However, they only represent this definition as a propositional rule indexed with time. So I mean, of course, they are not very suitable to represent in a OWL model as such, and also I think that definition-wise they are very difficult to represent or translate in a natural language as such. Well, apart from that, some other research, of course, somehow mentioned this joining operation, however, not rigorously. So our effort will be to find some rigorous definition of this joining operation based on in-depth characterization. But then what is important is that we try to build something I call inferred taxonomy, not an explicit taxonomy. The difference is that in explicit taxonomy, the subsumptions relationship, that subclasses are explicitly asserted in the ontology. Whereas in inferred taxonomy, we just define the concept and then run reasoners so that the subsumption relationships kind of inferred by these reasoning algorithms. And what I follow, I mean, there is no standard method for this, but what I follow is that first we need to identify the traits, and then for those traits we need to characterize the different concepts which are part of the taxonomy. Then of course design the taxonomy or develop it in a preferred language, and then of course run reasoner to find the inferred taxonomy. Now, going to the first step, what is the trait of the joining operation? So I start with three. One is that, okay, of course, each type of joining operations. Now, I mean, here I am already going into the subclasses of joining operation because it's easier to describe it. So, as we know that the common type of joining operations are, say, welding, soldering, brazing, bonding, fastening, all of this. So we can observe that all of these different joining operation actually produce different types of joints. So the output type is, I mean, different for this different joining operation. Also, if we go inside it, the sub-processes are different for different types of, I mean, it is a different strategy for different types of joining operation. And then, of course, if the strategy is different, it's very easy that, of course, we need different types of resources for this different type of joining operation. So we have three traits here. One trait is the output type, I mean, what type of joint it is producing. Another is what type of sub-processes are happening, so the strategy. Another is the specific resources. Now, we first come to the joint type. Now, what is joint is, of course, we know that in literature, the joint is something which actually restricts the relative movement or degrees of freedom between the components of an assembly. But how this constraint happens? So there, we observe there are three reasons for. I mean, three different reasons. I mean, say for example, there can be a continuity of material. So of course, the components cannot move with respect to each other. Then there can be an additional material holding them together. So there cannot be there cannot be free movement. And the last one is that their unique shape, how they are placed, with their unique shape, kind of give the constraint that they cannot move. So keeping this in mind, actually we can see that the first time where the continuity of material is there, it's actually from the welding process. And then soldering, bonding, fastening, they actually use an external material. And the fitting, what we call fitting, we actually do not use any external material. It's just a shape which helps in which actually put the constraint of the relative movement. So now we are trying to now formalize it. So we have this one predicate called has connector. So it is kind of relating an assembly, or it. I mean, at this time we can just say it is a material entity, and the particular connection between them. So we are actually giving it a special treatment or existence of that particular connection, and we call it hash connector. The hash connector is defined as such that, of course, it joins two components. Now it is for simplicity just two components, but we can extend this axiom for three or more. I mean, if you want. For simplicity, say it actually joins two components, and then the resulting assembly is such that that every material is either from the input parts or this joint. So there is nothing else but this component and the joint. Now we define that what is this tripartite relation called joints. Now here again it is for just two components, but you can extend it. I mean, you can extend it for XYZ and as many as you want. I mean, so what it says that, so now here we are bringing some medio-topological concept, and then we are using the medio-topological model given by Dr. Smith. It's not the RCCA, to be clear about it. So what we say that this joint, you can say it is a joint, but still I am saying it is a material entity, that some portion of the joint either straddles one of the component or say both components. But then if they are touching both components, then they are in different portion of the joint. And then we use the predicate straddles. So straddles has a very formal definition. I'm not going in there. You can say that it is either the boundary or the touching. I mean, it's just touching at tangent or the boundary. Now, to formalize it a little bit, I'm not going there too much, but to say that we also kind of try to define it in terms of how it is related to the mating boundary. So mating boundary is a very popular concept in any kind of joint. And then mating boundary, we actually borrowed it from Kim's definition. He used a definite descriptor. So the iota operator we wanted to remove, and then we used a tripartite predicate for that. Not going in there, but it is very similar to Kim's formulation. Now, if we have that, then what we can say is that joint, first of all, from the previous axiom, you can see that at least there is some boundary of that joint, the gray portion, which is not a bona fide boundary. So if there exists some portion which is not bona fide, we can say that it is a fiat object part. So we say that joint is a fiat object part, and of course it is very much, I mean, common sense that there has to be a mechanical assembly which has the connector as the joint. And then also on the other hand, that every mechanical assembly needs to have at least one joint. I mean, otherwise how can the component are connected? Now we have this definition, and then this is a major departure from the common sense notion of how joining happens. We are saying that joining process will produce at least one joint. I mean, also there is something like it will only produce joint. Now, of course, you can tell me that there can be some byproduct which are also output, not joint, maybe. But we can differentiate that with some other predicate. Say for has output, it is only joint. Now, if we have the definition of joint, then we can actually formalize three types of joint. So we call it joint type 1, simply that some portion of that joint, some material, it actually comes from the component. So it is very typical for say a welding process, and where some materials are fused to make the joint actually, but then other things comes from the filler metal and then stuff like that. And of course, there is a second type of joint where none of the portion of the, no portion of the joint is actually the part of the component. It comes from outside. It is an external thing. Now, what is the external thing? Based on that, we can define brazing and soldering. Brazing and soldering both uses this external material called filler metal. So we cannot differentiate. But say, okay, for now, it say that brazing and soldering uses filler metal, fastening uses fastener. Fasteners are say nail, clips, screws, etc. And then bonding uses, bonding uses adhesive. So with the type of the external material, we can differentiate between them. And then, of course, we'll come to that, how to differentiate brazing and soldering. They are very similar, but then you need to go to the process characteristics to actually differentiate them. Now the last type of joint is where all the material are actually, if there is no joint actually, it is a joint free. But then how we can formalize it, say that everything what makes the joint is either part of the, part of one of the component or both the component. So it is typically is the output of a fitting operation. Now we define the output type of the joining operation. Now we are going into the process characteristics. Now, to define the process characteristics, to formalize the process characteristics, there is a problem that welding, soldering, brazing are a kind of continuous process, whereas say fastening, say you just hammer a nail. This is kind of like a discrete process. So we can have one method, the first method, where we can use the unit process to actually characterize this type of continuous process. I'm not going into detail because I do not have much time, but then if we just try to characterize the unit process, this is one example from the welding. So we can do a detailed characterization like that every welding process you actually apply heat in some kind of way, which actually melt the metals and also the filler metal and some other things like the slugs and stuff like that. Then you have a solidification process. And then, so there are these three sub-processes, that heating, melting, and then solidifying. And then there is a precedence among them, that the heating needs to happen before melting, and the melting needs to happen before solidifying. But I'm not going into the brazing, I do not have time. But then there is another way to do that, this unique process is not very, it's very cumbersome to use. But then we can say that we are not interested in characterizing the actual process, but we can actually specify a plan for the process. So it's the process specification, you can say. And then this is very helpful in a sense, like Industrial Ontology Foundry gave an initial model which we can use to define this kind of process specification, and they call it plan specification actually. So how it happens that we then say that welding process is something like where it is a planned process. It is not the actual process. It's a planned process which is specified or prescribed by a welding specification. Then you go to welding specification and then say that, okay, there are different sub-specification. And then, of course, Industrial Ontology Foundry has that. Industrial Ontology Foundry will actually have a talk after that. Oh, okay.
Try to talk.
Oh, okay. Now I can hear. Yes, right. Yeah. So And then you can define those sub-processes as something what industrial ontology found it calls action specification. Of course, the action specification then can point to the actual process, and then you can define the precedence and then also the resources needed, with them. So some approximation was needed to actually make that encoded into OWL, because in the end we have to use OWL. Not going into the detail is very easy. It's kind of approximation. Most of the, we tried our best to keep the original formulation as much as possible. Then, of course, there are other now lower level of this, taxonomy, which are basically classified based on the consumable, the types of resources, the machine, tool, and different types of sub-processes, which makes the taxonomy. Not going into Brazing. Okay, so now coming to the last part, that how this infer taxonomy works, and then you can see that it's not very visible in a way. What I meant to say is that, okay, the definition written for a particular welding process, say for example, uses the other taxonomies to define the subsumption relationship between these processes. So that is all about it. And then in the end, then we actually have the complete taxonomy. Now, of course, it is only the result of the inference. However, we tried to compare it with the standard taxonomy for the joining operation, which are used in the industry. There are many books which publish that. It of course matches almost, like I will say, 95%. There are some differences, but we have we have justification for those differences. And of course, this is not tested on actual data. Of course, taxonomy is not supposed to be tested like that. The inference actually proves some of the point, but then for practical usage, of course, we need to test it with actual data. Coming from the assembly operations, and then model it and see that if the definition works or not. In future, of course, we will try to model, say, joint type, the thickness, and then there are some different type of defects which can happen in the joint, surface finish, and then capabilities and all sort of other things. So that is all for now, and then I am open to questions.
Thank you very much. Is there any question from the audience? Yes. Maybe I can bring you the micro.
Oh,
Thank you, Paul. Very interesting insights on manufacturing functions, which I also mentioned earlier. That's for us at a certain point. I was just wondering what's exactly the purpose of the work. You were distinguishing between like the explicit taxonomy from the implicit one. So once I have the taxonomy, many users are fine with that, but you model a lot of details that lead to deriving the taxonomy from that. So what are the use cases? Do you envision systems where you observe a certain situations of what has been going on, and then a system automatically classifies what function was being carried out? Is that what you want to do? Or, because in a lot of cases, I would be fine with having the taxonomy like itself.
Of course. So of course, in some cases, the explicit taxonomy will work. I feel that, of course, we do not have an use case to prove, as I say, that we did not model data to it, and that will be the next work. But then I can give you an example where this type of detailed process characterization will be very much helpful. For example, that you can see that welding has a problem of, say, brittle welding, because there are a lot of bubbles forming between, and it happens because of some kind of problem in the solidification process. So the so that like the temperature is like instant cooling or something like that. If it happens, so the bubble forms. So if you want to really write rule, for example, to automatically detect, okay, if you have this kind of problem, some defect in your joint, how can you try to identify the process where it actually started? Then if you have data, then you can actually identify which resource was used in that particular process, who actually made that welding, and who were, in charge of that. So, this is a very good use case where you can use this process characterization.
Okay, I see. Maybe just a direct follow-up question to that, if I may. Like you mentioned a breakdown of the process into phase and what happens first, and then does this also imply that you have to break down the function itself and splitting up welding into the bits and pieces?
Yeah, very much. That is why it's so interesting. So, for example, that you have some consumable you need to use for, say, in the welding, you need to use some inert gas. Say, say my G is like an inert gas flows around the welding torch or supplied from outside. It actually helps in like protecting the weld from the outside, environment, and only happens during the solidification and the melting also. So melting and solidification. So the function of that particular resource, the inert gas or say slug or something like that, is now, of course, realized by the process of melting and the solidification. Of course, not exactly melting and solidification, is actually creates a protective layer. So that's okay. You can create another process to actually model that I want to create a protective layering, or say protecting, or say layering, or something like that. Shielding is the very good word, probably. So that function of shielding is realized in those processes of that inert gas.
Okay, thank you. Is there any other question from the audience? I don't know whether online there are questions. Let's check. Not for the moment. Last call for question. Don't be shy. Well, actually, I have a clarification question. Let's say I'm not an expert of mirror topology, but so most of the notions that you discuss are actually relations, right? While then in the taxonomy, you show a lot of elements which are probably classes in the old in the old version, right?
Yes.
So how did you model the relationship then between the taxonomy from the class point of view and then the relationship from a mirror topological point of view?
Yes, very good question, actually. Extremely good question. So I used Barry Smith's media topology, which is about space. Now, of course, then all the media topological relationship will hold between space. However, then here they are kind of adopted for solid object. So but then it is not a problem as long as you do not mix up solid object and empty space. There are some work with Pahar Ameri and then Michael Gruninger, and then they actually showed that, okay, there are a lot of problem if you mix up empty space and then solid object. But then here I only encountered, I only considered solid, object. You can consider them as a space, and all the relationship holds between the spaces.
Okay, so when you talk about fastening, brazing, they're really material entity, which puts...
Yes, all the material entities are, you can say, solid object here. Right. And so all the medio topological relationship will hold between them.
I see. Yeah. Okay, thank you very much. Is there any other question from the audience? Yeah, maybe we have a quick question. There's a line one, sorry. Is your ontology aligned to Dolce or any upper level ontology? I think that you mentioned this.
Yes. I say it is right now, I can say it is 90% aligned to IOF core, which is adopting BFO. So, yeah.
Okay.
but then some are not there. Say, for example, this medio-topological relation. Also, I use some thematic rules to distinguish between the participatory roles. So, and they are not there in the IOF4 or PA4 right now. But yeah, I mean, 90%.
Okay, let's start up again. Thank you very much.
Thank you.
So for people present here, we now have a coffee break. We're a bit late, but it's fine. We come back in 15 minutes, so 11:45. And for people joining online, we will break and we start again in 15 minutes. Thank you.